Okie dilly doddly. So we're getting pretty close to being done with Unit 2. We won't get done with it today. Maybe Friday, maybe. But we're getting close. So what we saw was that we have a whole lot of imbalance, right, within our leagues in terms of revenue, payroll, winning, however it is that you want to look at it. Right? And to a large degree, a lot of this imbalance persists. So what we want to do is we want to see, okay, well, how can we actually measure this imbalance? So what are the different ways that we have created to do this? Right, we have 7. So one of these is the Gini coefficient. So if you've had any other classes, these are usually any other econ classes, we use this a lot to measure imbalance. It's usually used in terms of income inequality. But we can use it to measure revenue and payroll. And don't forget that this Gini coefficient lies between 0 and 1. So the larger the number, the more inequality. So let's kind of review what this guy is. You've got, say, and this can be for anything. So let's do our percent of the population here. Over here we could have, say, percent of revenue. Or if we're doing people, percent of income. Or if we're doing payroll, percent of payroll. It could be any number that you want it to be. Anything that you want to look at. Right? And so, let's see if I can get this actually fairly. This looks to be about halfway right here. 25. I think it looks pretty approximate. And then up here we've got basically a 45-degree line. So here's our 45-degree line, right? And then up here. Okay? So here is our percent of revenue, right? So this is teams. So here's our teams. If we have perfect equality, I mean, here's in essence is what's happening. We're lining everybody up. Team A, Team B, Team C, Team D, Team E, Team F, Team G, Team H, Team I, J, K, L, and O. We're lining everyone up. And we're saying, oh, okay, here's the first 25%. Here's the second 25%. Here's the third 25%. Here's the fourth 25%. Right? This is what we're doing. If we have perfect equality, 25% of the revenue is going to be captured by 25% of the teams. 50% of the revenue will be captured by 50%. Right? 75% of the revenue will be captured by 75% of the teams. So, and that would be on this line. Right? But we don't have it. You've got something that kind of looks like this. This is called the Lorenz curve. Here is here's your Lorenz curve, right? And we've got these two areas here, area A, area B, and the Gini coefficient just this area A divided by the area A plus B. So you can see if you're really, 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 really close to the line, so this could be some number, right? I mean, that's all that this is. This is just a number. Whatever the number is. Right. If you're really close to the line, area A is really small. Right? Area A plus B is going to be equal to 1. And if A is really, really small, then the number is really, really small. If A is really, really large, and B is really small, then it's getting closer and closer to 1. A is almost the whole area. And so you can see what happens here. I mean, here you've got 25% of the teams that make 50% of the revenue. 50% of the teams with 15% of the revenue. 75% of the teams take total revenue of 22% of the revenue. Which means this last 25% of teams has, whatever, 78 something. 77.7% of the revenue, basically, is what that means. I mean, we can use this in all kinds of different ways. So here is, say, Bangladesh. Here's the U.S. All right. There's your bottom 20% of the population, and your second 20%. Your third 20%. Your fourth 20%. Top 20%, right? So if we want to know, okay, what percent of the population, or what percent, here's these, we divide the population into 5 different groups by 20. And if we want to know, like, say, income before taxes and cash transfers and welfare and all that stuff, this is say 3.4, this is say 12.5, this is say 8.7. This is say 16, this is say 14.8, this is say 20, this is 23.4, this is 4. So if you're looking at this in terms of, say, income, right, what this says is that, oh, look, the bottom 20% in Bangladesh have 9% of the income. The bottom 20% in the US have 3.4%. The top 20% in Bangladesh have 41% of the income. The top 20% in the US have 49.8% of the income. Right? And you would use these, you basically plot these points on here. And that creates some area. And then you just calculate the Gini coefficient. Right? So for example, for here, for Bangladesh, this Gini is 3.18. For the US, it's 0.4. Right? You see that there's more income inequality in the U.S. than there is in, say, Bangladesh. You can also use them for baseball and payroll and all that kind of stuff. And so, and this is actually in your book, but I'm not going to. I can never get that thing to work. All right. Oh, wait a minute. So if we look at these coefficients over time, here we see see Gini coefficients. These are based upon payroll. And these start in the started, say, the 1950s, where you've got EOS, end of season, American League, EOS, end of season, National League, end of season, right? OD, opening day, NBA, NFL, and NHL, right? And so you see the NHL here in the 1950s average about 0.1. Down here, the 2000s average is 0.205, right? So payroll has become more equal or less equal than the NHL? Less. You have the NFL here, though. It's in the 1950s, 0.194. And down here, in the 2000s, on average, now their Gini's 0.07. So the NFL has become a whole lot more equal. And you have things like the NBA, 0.16 in the 50s, 0.17 in the 2000s, basically stayed the same. National League, 0.11 in the 50s, today 0.198. It's getting more unequal. American League, 0.14, 0.225 in the 2000s. Why do you think it might be more unequal in American League than in National? What's the difference between the American League and the National League? Designated hitter, right? So in the National League, your pitcher pitches and he hits. In the American League, your pitcher pitches and he doesn't hit. You got the designated hitter. And then you can see those in the season ones there. But so you can see that we've seen these changes. It looks like the largest one that you had here in the NFL was probably, well, it was the 1950s. NHL. 2002 was the most unequal. NBA. The 2000s average. So we can measure that, right? We can do the same thing for revenue. So we see here American League, 0.241 in the 30s, National League 0.224, all the way down here to the 2000s, 0.16 and 0.14, right? So it's becoming more equal, right, generally speaking. NBA here, 0.214 down to 0.12, right? Also becoming more equal. Let's look at the NFL, 0.15, 0.072. Becoming very equal. NHL 0.15 in the 50s, 0.153 in the 2000s. Right? It's roughly the same, not changing that much. So you're saying some Gini coefficients for revenue and balance for American League and National League and the NBA are becoming a little bit more equal than they were, say, maybe in the 50s and 80s, but not quite as much as that you see in the NFL, right? The NFL is becoming very equal. And we'll kind of see why that is a little bit later on, some of the things that they've done about that. Let's look at some other measures of the balance that we have, because there's lots of them. We can look at within season. variation. And we can use this to look at basically the standard deviation. Of winning percentages. So we're going to have our standard deviation here. The summation I equals 1 to n WP CT IT minus 500 squared all over n. We're going to take the square root of this guy. So we've got our winning percentage for each of our teams in each of our given years minus 500. We're going to square that, add all that up, we're going to divide by the number of teams, and we're going to take the square root of that guy. And that's going to tell us the standard deviation, which is in essence what a standard, just a normal standard deviation that you have for any statistical series. So this WPCT here's our winning percent for team I, C's and T. And here is the number of teams in the league. So the larger this guy, the greater the dispersion. I.e. the larger the imbalance. Why don't we square this guy?
Because then it equals 0.
Yeah, exactly, right? Because if you look at, remember what the average is. It's always good to review basic statistics. If you've got this guy at one's at 0.600, remember you got a 2-team league. If one of the teams is at 600, the other one has to be at 400. 600 minus 500, and this guy is 100. That's negative 100. 100 plus negative 100 equals 0. All right? And all that doesn't make any sense. So we square that guy. Remember what's going on here with standard deviation and variance. Let's assume you can look at anything, how long it takes to get to class, right? So you know, on average, how many minutes it takes you to get to class, right? So here you are at your house. How long does it take you guys on average to get here from your home campus? 15 minutes, right? So here's your 15 minutes. Let's say you get there in 14 minutes. Is that a really big deal? Or is that not that big of a deal? Right? And that depends upon the variance, right? How much variance do you have? So if you're here at 15 minutes, if it kind of looks like this, here's say 14, here's say 13, here's say 16 minutes, here's 17 minutes. If you're over here at 14, that's a really good deal, right? You made it there really, really quickly. If it kind of looks like this, here's your average, there's 15, here's 14. That's not that far off. Right? It's not that big of a unit. So who said 15? So if it takes 15 on average, that means sometimes it takes more than that. How long would it be before you're like, oh my gosh, that took a long time?
Like 19 to 20 minutes.
Jack, 5 minute difference, right? Which means 5 minutes difference the other way. If she gets to class in 10 minutes, it's like, oh my gosh. All the lights were green, there was no traffic, it was really, really easy, right? What's the probability, Danielle, that you'd make it here in 8 minutes? Pretty small? There is some probability out here. 8. Right? But that probability down here is really, really, really small. And so in essence, what we're measuring is how much dispersion is there about the mean. If teams are really packed tightly, there's not a whole lot of variation. If there's a big variation, then we know that there's going to be a whole lot more variance, right? This right here has very little variance, and therefore a very small standard deviation. This guy right here has a lot of variance, right, and therefore a high standard deviation. It's really, really difficult to say. Both of those have the exact same average. But this person could be 8 minutes to, I'm making up a number here, 23 minutes, 95% of the time. This person here, 95% of the time, they're 13 minutes to 17 minutes. It's really, really, really tight. So we have this within season variation. So, let's look at the NBA. Here's the 04-05 season. We're going to look at the 08-09 season. Okay. So here is our Atlantic Division. Here's our Southeast Division. So in the Atlantic this year, we had Boston Celtics, we had Philly, the Sixers, we had the New Jersey Nets, we had Toronto, and we had New York Knicks. They didn't have a very good season there. Over here we had Miami, we had Washington, Orlando, Charlotte, and Atlanta. So the winning percent for these teams in that season, 0.549, 0.524, 0.512, 0.402, 0.402. Over here, 0.72, 0.549, 0.439, 0.22, 0.159. So even a cursory examination shows in this division, in this year, the 04-05 season, which of these two teams was more highly dispersed, which was less highly dispersed?
The Atlantic Division was less dispersed.
That 0.549 to 0.402. People are packed pretty tight in around 500. Over here, you're going all the way from 0.72. Miami won 72% of their games. It's pretty good. All the way down here to Atlanta, winning 16% of their games. It's a horrible season. All right? And so if we do this, 0.549 minus 0.5, 0.49 squared, plus 0.524 minus 0.5, 0.024 squared, plus .512 minus 0.012 squared plus 0.402 minus 500, 0.098 squared plus 0.098 squared. Add all that up, divide by 5. We're going to get here 0.0666. Over here, same thing, 0.72 minus 0.5, square that, plus 0.549 minus 0.500, square that, plus 0.439 minus 500, square that, plus 0.22 minus 500, plus 0.159 minus 500, square all that. Standard deviation of 1% for the Southeast Division that year is 0.223. For the Atlantic Division, 0.068. Right? 4 times as much dispersion as you have here. And you can do this for anything, right? You can do it for payroll. You can do it for whatever, it could be anything. And then if you look at the 08-09 season, .756, 0.500, 0.415, 0.402, 0.39, and over here, 0.720, 0.232, 0.524, 0.427, 0.5, it's a 7. Southeast still has more dispersion,
The Atlantic Division almost doubled.
but the Atlantic almost doubled. Exactly. And in the Southeast, it actually went down. The problem with this is, what do you do about the length of the season? A short season, you're more likely to have more imbalance. Take football, for example. How many games are played in football? 16. Right? How hard is it to win 16 games? It's hard, but it's not impossible, right? I mean, look, did the Chiefs win the last game? So they went 5-0, right? And that's pretty good. How many games in baseball? 162. How hard is it to win 162 games? That's very difficult. And so even if you're going to have just a random flip of the coin, you're going to have these types of problems. So as you can see here, let's see how many times we can get this. So here's a coin flipper. We can select, let's select a US dollar. You can select anything you want it to be. But, let's just select the board. So if I have 10 virtual flips, I should have, roughly speaking, 5 and 5, right? That's what we're all taught, right? One, two, three, four, five, six, seven. So I got 7 heads. Three tails. One, two, three. Here's backwards. 3 heads, 7 tails. Let's do it again. 1, 2, 3, 4, 5, 6, and 4. One, two, three, four, five. 1, 2, 3, 4, 5. 5 and 5. One, 2, 3, 4, 5, 6, and 4. I don't know if this tells us the numbers. I'm not going to sit here and calculate all these up. That would be stupid. But do you think this is more likely to be 100 and 100?
Yeah.
I mean, do you think this is going to be, there was 200 flips. How likely do you think this is 140 heads and 60 tails? Less likely, right? Whatever this number is, and I don't know what this is, it's just some number. I wish it told you at the bottom. I thought it did, but maybe I was wrong. Same thing here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 5, 6, 7, 8, 9, 70, 1, 2, 3, 4, 5, 6, 7, 8, 9, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 2, 3, 4, 5, 6, 7. You do that again, it's much more likely to do this. So you're going to have more variation the longer the season. I'll pick it up from there on time.